The talk I'm going to give to you today is not a typical HPC talk. So in this talk, I'm going to give you an example where HPC has enabled to develop a technology that gave us a capability that is basically never available to us before. The actual implementation of this technology in HPCs and the recent implementation of that in GPUs will be given by a talk tomorrow in 12:20 o'clock by my associate, Martin Cornell. He's sitting somewhere here. So please join his talk if you want to know the details of the implementation of these technologies. Now, before I'm going to talk about the computational stratigraphy, which is the technology I'm going to tell you about today. And first, let me tell you a little bit about basically basically what we do as a geologist in subsurface. And the basic task for geologists in subsurface is to make predictions. And the data that's available to us are different kind of data. It could be seismic, it could be well-line logs, it could be cores, and if the field has already in production, they will have different kind of engineering data comes in. And the prediction we want to make is everything related to business in terms of where we need to understand the subsurface distributions of reservoirs, the sand, the shales, and the flow buffer and the barriers. And also we want to understand basically the accurate characterization of the uncertainties around those predictions. So usually the process we're making this prediction is using the data, but we need to integrate those data in some kind of model. Those models can be conceptual models, the model can be computational models, or it could be any model. But those, you have to have some framework where those different types of data can be integrated. And then we make predictions. Now, increasingly, as basically our reservoirs are happening in much more challenging places, that means that we start to explore much deeper. And we explore them in a geological more challenging places, for example, sub-salt, and our seismic qualities become more challenging. And when we move towards more deeper environment, and we drill less wells, so our well density becomes less, so our data becomes less. So it makes those predictions much more challenging. But also that from industrial studies, and you can see from this figure, that the things that really affects our basic EUR predictions, that basically is that you have EUR stands for estimate ultimate recovery. It basically says that how much you estimate this field can produce. And from actually what is produced, there's a variance of EUR. And this variance, we want to minimize this variance because if there's a huge variance, that means any kind of decision you make is not accurate, right? So you want to minimize variance. So in industry, there is a periodic look-backs. And when you look backs, and you can see the contributing effect that basically affects EUR variance, and the reservoir connectivity is the most, reservoir distribution and the quality is the second. So these are the biggest basically challenges. Then we ask ourselves a question. We say, so why we can't predict those basically EUR more accurately? And I summarize here as 3 different challenges. One is basically data challenges we already talked about, and the second is I think there's a science challenge also. You know, geology is a very basically is not a exact quantitative science. It's a very qualitative and empirical science. And fundamentally, in a very simplistic pictures, and the way geology works is that you make observations, and you make as much observations as you can, and then you start to categorize those observations, and you see these observations, these data are similar, etc. And you develop conceptual models. And with the conceptual model being built, and you will basically iterate back, looking at a different data, say, okay, this data belongs in my conceptual model, in my concept, it belongs to certain different places. And in this figure basically shows that you can have different rocks, basically different cores from different places, and you have some conceptual model of how your depositional environment will basically form. Here's a delta, basically you have proximal delta, you have a median, you have outer deltas. and you put those well-logged observations in different places, and you categorize them. Once you categorize them under your framework of your concept, then when you want to apply them, you have new data comes in, you compare with your category, essentially your concept. And then you say, okay, this data looks more similar to this. Thus, this particular location is similar to all the wells, all the well locations I found here. Thus, it is somewhere here in the depositional system. Then you can make assertions of predictions of things away from basically your well locations. So that's essentially how geology works. There's seismic. Seismic does give you three-dimensional basic predictions, but it has its own basic challenges, mainly is from resolutions. And here you can see that a 25 Hz basically wavelet, basically that is the minimum resolution, maximum resolution it can resolve, but it's laid basically on top of an outcrop, and you can see all these variabilities and heterogeneities that show in this outcrop cannot be represented by this simple wavelet. And if you look at the scale, and this is plot one-on-one, this is Chevron building, and essentially you are talking about 20 floors of buildings. That's the best you can resolve from seismics, right? But the actual heterogeneity features that affect the reservoir flows is much more in a much finer basically resolution than that. And there's also another I call the technology challenges, right? So even you know everything, let's say assumption that for some reason you obtain exact basic distributions of subsurface. You know where the sand distribution of sand is. You know where the shale is at, etc. Our current modeling technologies are still not able to represent them effectively in our 3D models. What do I mean about that? So here, what the movie you are seeing here essentially is a reservoir. Then we take all the sand away. And the sand is where it contains the oil. You take the sand away, then what's left is all the shales. Those shales are flow background barriers. And the flow background barriers, that means that if you drill a well, that to a volume of sand, if this volume of sand is separated by this continuous basically shale background barriers, it is very difficult to drain the oil that in the sand, that in the neighboring sand, that's separated by this flow background barriers. So for design of basically well locations and design of basically to optimize the production, and you really need to know where you want to drill wells. And in order to know that, you need to know detailed basic distribution and of this kind of shale barriers. And the classic, basically, commonly used industrial basic modeling tool is all geostats based. Geostats is developed in basically mining industries. Mining industry cares most about volumetrics. So geostats is doing very well with volumetrics. However, geostats has a very hard time to represent this continuous surface. And that's very clear because in order to represent a continuous surface, essentially you can see here, like if all of them you want to fill with a shale, even you put 90% probability of shale for each cells, and for 4 of them to all be shale, that's 0.9 to the power of 4. And you're looking at the very low probabilities. If you want to have a patch of 100 cells, you want to all be basically deposited by shale. It's almost impossible because you always have holes. That's why traditionally, the current basically modeling technology is always we call the overly homogenize the subsurface, basically. So you make wrong predictions, and we will show you just a little bit later. So the solution we have basically for really to address those challenges is really think that can we look at all this problem differently? And the way we choose is that to look at those basically to introduce physics to understand those geological processes and to make basically predictions. And the rationale behind this is that a lot of geometries that we care as important to us in subsurface, they are formed by basically physical processes. And also geology may vary from one place to other place. Physics is universal. And geology of a particular geological time period may be different from another basically time period. Physics is universal, right? So the idea is that if you can model the physics accurately, then you can capture those geometries and the spatial distributions accurately. To be very, very, computational stratigraphy is a technology system that composes many, many different components. So in the core of that is a physics engine to simulate geological processes that are leading to the formation of basically different depositional systems. And around that is all different kinds of technologies to facilitate applications and to reservoir characterization, reservoir modeling, and to basically to assimilate the data we have from field, etc. Okay, but today I'm going to focus on the core part of this technology, that is the physics engine of computational stratigraphy. And in the core of the core is basically a simple set of equations you see here. This essentially is the form of this equation is very similar to a standard Shuttleworth equations. But it was basically more complicated, those basically source terms. These are basically can itself be a functions of those variables. So it is this equation itself can be quite stiff. And we're not going to go into a lot of details of that. That essentially basically calculates basically the flow basically that transport sediments and leading to the formation of those depositional systems. Okay, and this part set of equation and with its basically source terms, I think I have a hard time to point to it. With these source terms, and it is implemented originally in basically the in a basic distributed system and using MPI as a mixed MPI and open MPI architectures. And recently we just basically rewrote the whole code and implemented everything in the GPU code. And Martin will be talking about basically tomorrow. So here, let me show you some examples. What you're seeing basically is a result of basically simulation that we described in the previous slide. And here what you're seeing is basically evolution of a deep water fan. And what you're seeing is a changing of topographies. And those changing of topographies are basically a result of basically turbidite flows in ancient times. They transport sediments and deposit in basically sedimentary basins. And the warm color represents higher topographies, and the blue color represents basically lower topographies. And here you can see there's multiple processes going on here. Essentially in geology we call, you have basically progradation. Essentially you have basically channel extends itself and transport a lot of sediments to the basically downstream of the stream. And then basically the channel ends, right? Because no one built the channel. Channel has to be built by process itself. And then flow expands. When flow expands, it dumps all the sediments. Because when flow expands, you cannot basically confine the flow anymore, and the flow velocity drops, and the sediments being dropped. Then it will form channel mouth bars in front of channels, and the whole thing backsteps. And when the flow feels more resistance, it will avulse to other places. Right, so a lot of basically our oil reservoirs are associated with like in Gulf of Mexico is very often in these areas, and in West Africa there's a lot of basically channelizer systems. We find a lot of basically where the reservoir is. Okay, from computational point of view, those avulsion can be very stiff process because you have to deal with dry nodes, wet nodes, etc. You have to make sure all those. It's actually very complicated to get those things right, and your code is very, very easy to blow up. And to make a simulation like this work, essentially you have to ensure that it's absolutely stable, basically. It changes topography all the time. Boundary condition changes everywhere. And you need to run for hundreds of millions of iterations sometimes. So that is basically where the computational challenge is. And that's where basically HPC become really important for something like this to be developed. And here is basically stratigraphy such a program can produce. And here the bright yellow shows basically medium, shows high quality sand, and basically gray scale of color shows different mud and shales, okay, of a different spectrum. And here the units here is a micron, And you can see this is a cut. Here shows the location of a cut in this figure. And here in the top figure is more from the proximal place. And you can see there's a lot of basically channels cutting into each other. And then you can see the specific patterns of how channels are stacked and their relationship to each other. And you can also see basically a different quality of sands that fill the channels and the different quality sands within the channel versus the sand around the channels. And these are very important knowledges for basically reservoir characterization and modeling. And you need to capture that in order to make sure that your subsurface model accurately represent what it is for production. And here then the second figure that comes down is become more medium and more distal. As you go to more distal, you can see there's more and more shells. You'll see a lot of more basically grayish shell stuff. And when you go to very distal, it's almost all shells. But if you go very, very close to the screen, I don't know if you can see there, even with those shells, they're not just a laminar, basically simply stacked. They have internal architectures. And those internal architectures are actually really important because in our MCBO businesses, these internal architectures and the fine details of how are they basically stacked really affects, for example, your fracture patterns, your frac patterns. And it really basically affects basically the efficiency of how much oil you can get out from those places. So these are very important basic information. Here is just a different view of stratigraphies, and then you can see this is a dip view, and you can see the 3 line on top of there. And one thing is really important is that what HPC has enabled here is that the realism that this type of model can provide geologists. And that's for the first time they can actually they can take a well log from a model like this. They can drill a hole there numerically, and they can take it to basically to other geologists. I did this exercise, and they don't know it is a model. And that is why you can compare the real well log so well, then you can really make basically, you can not only model the system, but you can learn the system from a model like this. That's why the HPC is so important. And here it shows you basically a different example. And this is a fluvial deltatic system. It's no longer a deep water system. And you can see basically a channel comes out, and the bluish stuff over there is a standing body of water. You can think it's the ocean. And the ocean level is changing, and you can see the depositional system happening there. Now, what's the new capability a system like this provides us is that you can see as the deposition evolves, and you can see this is stratigraphy. That is the lower figure, and those numbers 1, 2, 3, 4, 5 represents 1, 2, 3, 4, 5 in that map view showing in the upper left part of the figure. It shows basically how those rocks being formed in real time as the whole system evolved, right? And on the right figure, it shows the well logs, how those well logs being built up. So by going through this, you will understand a specific well log patterns, what they exactly means. So when you go to basically real well logs, then now you have a recognition criterion contains not only possibly spatial geometries of that, but also tells you the history of how this part of rock is being built. Knowing that, it allows you to predict basically much more accurately in the subsurface space, okay? Being a physics-based model, it has lots of advantages. A lot of things, for example, this is the wave-dominated deltas. And in geology, you will say wave-dominated deltas is completely different from fluvial-dominated deltas. They're 2 different systems. But in physics, they're just the same. It's sediment, the water transport sediment. The difference is the boundary conditions. You just implement the wave boundary conditions, and you can see immediately this one you can see the delta forms on this one is very different from the previous deltas. It has less branches, and you can see that the basically strand planes being formed and hosting basically progress. And we cut these kind of basically the numerical deposits. We compare the real wave, basically outcrops from the real wave deposits. They're almost identical. And there's lots of features. So a lot of features, geologists will have different names. And they say, how do you put that in? I tell them, I didn't put them in. It formed all by itself, right? So that is the power of basically a realistic physics model enabled by HPC technologies. And the lower image simulation is a similar simulation of this one, but here the water level is rising. As you can see, water level is rising, and the previous deposits are being eroded. And now you can see that the water starting invaded to here. It's starting forming barrier island. So here's your Galveston, but it's going to be disappear very, very soon, okay? So, so that's a forward model. That is basically the physics engine that develop all these basically results. And we call basically the numerical deposits formed by this one we call digital analogs. So now the question is that how do we utilize them to build our reservoir models? And a key condition of a reservoir model is that you have to be able to condition to all the wells, right? So let's say you already drill a well, you want to make sure your model at this particular location is exactly the same as your wells. And we have developed basically a workflows to, and technologies to address that. So I'm not going to go through a really basic detailed description, but a very innovative technology we basically created is called learned stratigraphy simulations. Essentially, we use forward model results as digital analogs. We transform those things into so-called K-layer space, and the K-layer space essentially is that you can think about models in XYZ real space. You have X, Y, and the vertical direction is Z. And we already talked about statistical models or any models that has statistical component in that you can make holes, right? But computational stratigraphy has the ability basically to essentially to convolve the third direction into, we say, a pseudo-time direction. We call it K-layer space. So at that time, cell thickness become a parameter instead of a cell geometry. So one volume become two volumes here. And so we can do basically either machine learning based algorithm or some geostats algorithms, but taking the patterns and distributions from digital analogs and populate that and transform back into real space, essentially. Then I initially expanded in the time space, because every single layer is continuous. And I did all my property-based populations, including my thickness populations. Then I compressed back. It's almost like you compress from a signal to basically the frequency space, and you do everything, then you come back. It's the same transformation, but here is more basically three-dimensional, basically a time transformation. And you can see the result here, basically. So this is the original Computational digital analog. So that is a model created directly from the forward model. And this one is reproduced from basically this method. You're going through basically this modeling workflows. And you can see that distribution is very, very similar. And even more, you can compare basically, this one is basically all conditioned to 10 wells. You have 5 injection wells and 5 basic production wells. And you can see the flow response exactly top on, right? But if you compare with existing modeling technology, here's all basic MPS. That's the current industry commonly used method. And then you can see this model has a very, very different basically water production curve from that. And why we believe our model is better, because in a lot of reservoir simulations, the common problem we encounter is that we can't predict basically water breaks. We have early water breakthroughs than we predicted. That means that our model is overly uniform. We can't predict rapid water breakthroughs because it lacks organized basic heterogeneity in space, and which that is provided by our model. And you can see that we predict, because this points, the earlier that means your water breakthrough earlier. So we capture basically early water breakthrough better than the existing reservoir modeling method. And we also apply, so this technology in Chevron has been applied to many, many business units, including basically the Chevron New Energy business units. And we found out that this model has even higher impact in terms of our basically predictions of CO2 plume migrations than basically conventional oil basically flows. Okay, so what I'm saying that, so we did a test. So here's a Computational model, And here is basically a MPS model. We utilized the component expert and did everything they can, try to reproduce this one. Except MPS model, as I told you, it's very leaky. Even you hand draw things there, here and there, by the time you do property distributions, they're very leaky. You can never generate a continuous surface in the sense that they always have the holes because by the nature of its statistical-based algorithms, okay? And then we basically did CO2 injection for 30 years, and then we let it stop, and then we want to see where the CO2 plume goes in 100 years, in 200 years, right? And you can see this is Computational model results. This is standard MPS model results. And if you first compare with this figure, you see in 30 years injection, the model best, we tried our best. We make our model like a volumetric distribution really similar to us. It's not that different. It's somewhat different, but not that different. And then when you look at the 100 years, you'll see that Computational model basically retains all the heterogeneities and the continuous organization of those heterogeneities. Those CO2 plumes are being preserved very well. And you can see MPS model because it's what we talk about basically is the over-homogenize of the model. So essentially those continuous shell layers, you can't represent them basically with the integrity you need. And it is starting artificially generate artifacts, so allows basically CO2 to migrate upwards. And you look at after 200 years, you can see that here you still have very realistic retaining of CO2s in different layers of the reservoir we inject to. And this is the prediction from the existing models. Everything is basically flow to the top, right? Here you can quantify this effect. And if you quantify this effect, you can see basically this blue color represents the total basically CO2 contained in the lower third of the reservoir, and the orange color represents total CO2 contained in the middle, and the gray represents the total CO2 basically retained on the top. And this bar graph shows the evolution over 30 years, 60 years, 100 years, 150 years, and 200 years. And you can see that for the Computational model, and it decays much slower in the bottom than basically the MPS existing industry standard model. And you can see basically the gray space is the top layer because it's an excessive amount of migration to the top. And you can see in the top, the CO2 basically, in the MPS model, because it's very leaky, you have accumulated a lot of CO2s over 200 years. And here, basically, you have less being basically accumulated. And this, of course, is a study basically we done on basically synthetic models. And some of those studies has been applied to basically real field, and there's 4Ds in some of our field, and they compare with the Computational model really well. All right, so I just want to conclude. Hopefully I didn't use more time than I was given. Basically, we think computational stratigraphy or all the technology like this, and really basically utilize HPC basic capabilities, and to basically introduce a lot of physics-based understanding of geological processes is essential for improving decision quality and accelerating basically the all subsurface characterization and modeling and decision-making process, okay? Because you introduce the physics, it bridges the gap between geophysical and the geological data. And if your model is very much based on first principles, and you can trust your model to a great extent, then if the model is geometrical based or basically some simple algorithmic based, okay? And then it provides basically new science and new insights into basic depositional systems, allows us to basically re-examine geology in a very different way. Because now, in addition to data, to our observations, our conceptual models, we can test our concept with a capability like this. And we can see they agree, not agree. If not agree, is that because data? Is that because of model? Is that because of concept? So in this integration and the iteration can really help us to advance our understanding of geological systems. And the other thing that's really important is that development of advanced workflows, such as LSS, I should talk about, this reservoir modeling workflows. That's really important, not only just to closing the technology gap in reservoir modeling in itself, is also really to bring the HPC product, the value, into our business. At the end of the day, we can make very beautiful simulations. If we cannot use it in our basically business, and it's harder to survive over a longer time. And I think the way to make it useful is really to integrate with existing workflows, or you develop similar workflows to replace, or basically to augment or to replace in longer term of existing workflows, and to make sure everyone can actually use it, and use it in different business scenarios everyone is at. It's very important. The last one, of course, is that we think rapid advancement, as I have been talking about this many times in this talk, is that we think it's really something is an enabling technology, and this is making a step changes in our subsurface basically prediction and modeling, and also, in my opinion, is also making a step change in geology as a whole. All right, so that's it.
Thank you very much, Tao. I think we have time for maybe 1 or 2 questions. Yeah, Telef. Or you want to start your presentation early?
Ooh, I could do that. That's an idea. Thank you very much for the wonderful presentation. It seems like what you want is, at some point, the model that's compatible with what you observe in your wells.
Yes.
Can you do that directly based on your physics simulations? Can you constrain them with the well information that you've observed? Or is it a repeated forward modeling, this didn't work, let's do it again and again and again process?
So this is a really good question. And we tried, and to be very honest with you, we failed. We failed is not because we don't know how to do it. We failed because it's very extremely computational intensive. It's so computational intensive, even with today's basic HPC capabilities, is harder to achieve. In a practical sense, I can make maybe one example, okay? But in my business, I needed to do it rapidly, I need to do it fast. What we find out in face of these challenges, what we find out is that we actually don't need to basically to exactly inversely model this system. What we find out 2 things. One is that those depositional systems, they generate basically stacking patterns, for example. The distribution of channels, for example, their heterogeneity architectures, they're very similar. So they're almost like a attractor in a dynamic system. And they, unless your boundary condition changes significantly, they move. Otherwise, those statistical properties, they remain fairly constant. Okay, so that is our friend. So instead of pursuing exact inversions, so the route we're going is that we develop an ensemble of digital analogs. So we more pursue a statistical understanding of those structures, heterogeneity structures, and find a way through developing innovative workflows like I told you here, and bring those structures into our models. So I would say it's the second best solution. But if one day that I really, my computer power increased another 1,000 times, I may try full inversion again.